So today we are going to continue talking about the relation between the Laplacian and the angular momentum operator. And what my hope is that I'll build up to a discussion on spherical harmonics. Okay, and but that will take a bit of discussion. So. Okay, so where do we begin? So the first thing to remind ourselves is that it's how the rotation works. Okay, so rotation works by applying the rotation operator. Now I'm just dealing with the coordinates. So xi is a rotation matrix applied to x prime j. And for small rotations, this tells you that, well, let's get it out first. Remember that this is e to the omega, and this is ij, x prime j. And for small omega, which basically means for small rotation angles, you can do a Taylor expansion. And by now, I hope that's familiar. What it means is basically this will give you connector ij, right? When there's no rotation, it's just identity, plus omega ij, and plus higher order terms, x contracted with x prime j. Okay, and remember that the key property here, because we're working with rotations, doesn't matter whether I put my indices up or down. So this is minus omega ji. Okay, it's antisymmetric, i.e. antisymmetric. So what you discover. What we're about to discover is the orbital angular momentum operator that we already found in 2 dimensions. Okay, and so I'm just going to write it down, and you'll see that actually, except for the symbol omega, almost everything else is the same with the 2-dimensional discussion that we had already. But let's do it. So what do I mean? So what I'm going to do is I'm going to apply the rotation operator, this guy, on the position eigencat. And then I'm going to project this rotated eigencat onto an arbitrary state. Okay? And so what we know is that this is going to be x prime I, because this is x prime I plus omega hat ij x prime j plus omega hat ij x prime j plus higher order terms on side. Okay? And of course, this is just nothing but a complex function of the coordinates, and I can do a Taylor expansion. This is x prime this is x prime psi plus the Taylor expansion of this is omega hat ij x prime j partial I. This is the free index here is I. So this is like doing x prime plus ai, where ai is this object here, and ai dotted into the gradient acting on x prime psi. Okay. I think I should put a prime here, just to denote the derivative. Now, what is this guy here? So this is also given by e to the minus I omega ij over 2 jij acting on x. Okay? And this in turn is basically x and then e to the I should say yeah, so let me just erase all the primes here, I'm sorry, because this is an active coordinate transformation. I'm taking x and I'm applying my rotation to it, and the rotation is defined through this equation here, but I don't have a prime here anymore, I'm sorry. This, and so now let's do this one. So this is e to the plus I over 2 omega ij jij x, oops, I'm sorry, psi. Okay. And what's happening is that you will discover, actually I should, since I use an omega here, I should use a big omega here. Big omega, yeah. And this is big omega. Remember that the omegas here are the parameters for the rotation itself. So even though now this is an operator, J is an operator, I still need to use the same rotation parameters. Okay? So what will happen then is, this is now, for small omegas, I can now expand psi, this is the identity operator, plus I over 2 omega ij, jij, plus higher order terms, psi. Okay? Again, this works for any d. Okay? Any d greater or equals to 2, remember. And so if you just compare the two, you see that we have on this line, we have x psi equals to, I'm sorry, plus omega at ij x I xj partial I x psi is equals to x psi plus I over 2 omega ij jij, oops, x jij psi. Okay. And in fact, what I'm going to do is I am going to, because this guy is symmetric, anti-symmetric, I'm going to write it in the following way. I'm going to pull out the 1/2 omega ij xi partial j, and first I'm going to swap the I'm sorry, this is ji. I'm going to swap the summation indices. They are dummy indices, so I can swap the dummy indices. So there will be plus omega ji, then this will be ij. Okay? But then, because this is anti-symmetric, I can now anti-symmetrize this and then pull it out. I mean, swap the indices and then pull it out. So what I get is the following. I get 1/2 omega ij x j partial I minus xi partial j, all acting on x side. The first term cancels out, and then what we have is just the second term. So at the second term, you have this guy must be equals to I over 2 omega ij x jij. So, okay, and what you discover is that therefore you can cancel out the minus, you can cancel out the 1/2 and the omega ij, because this is arbitrary, right? These are arbitrary rotation angles. So therefore, I can just multiply throughout by minus I, and I get the following. I get that x jij psi is equals to minus I x j partial I minus xi partial j acting on x side. Okay? Okay, so let me check it, but this is certainly the right operator. So you might recall that in 2D, so I need to check my sound. Is it minus or plus I? Anyway, so in 2D, you might recall that the 2D rotation operator, in fact, we derived was in fact minus I x1 partial 2 minus x2 partial 1. That's why I think I made a sign error here. And so what you see here is that this is just a generalization of, remember this is antisymmetric, so I is not equal to j. So if I and j were 1 and 2, then you would just recover the two-dimensional rotation operator. But now we've discovered that this works in all dimensions, right? So this thing works in all dimensions. And also, because you have a question for me? No? Okay. So, yeah, don't be shy. So also in 3D, remember that J12 is in fact J3 and that is minus I x 1 partial 2 minus x2 partial 1 x psi and so on. So you have x 1 3 and this would in fact be x minus j2 psi minus or plus I x1 partial 3 minus x3 partial 2 partial 1 and then finally you have x of j to 3 psi x j1 psi, and this is equals to minus I x x2 3 x2 partial 3 minus x3 partial 2, all acting on x side. Okay. Something is wrong with my sign. I'll come back to this problem. Okay, I think this should be a plus only. This should be a, because I write ij here and ji here, this should be, I believe it should be a plus, not a minus. But let me come back to that problem. So what you see is that this is called the orbital angular momentum operator. Angular momentum operator. And what we'll be using most are these guys. It will be J1, J2, J3, because this is what we care about most in, for quantum mechanics, like 3D quantum mechanics. Of course, you can do quantum mechanics in higher dimensions, but we won't do that here. So how is this all related to the Laplacian? So this is why I wanted to work it out in arbitrary dimensions, because the discussion here, at least the relation between angular momentum and the linear momentum holds in any dimension. In particular, it's really an expression of rotational symmetry again. Okay. So let me write it down for you guys. But what we discover is the following. In fact, it's a homework problem. What you discover is that the Laplacian minus the Laplacian is actually a force momentum squared. And this in turn is related to the angular momentum operator through the following. So it will be, the first part will just be the radial coordinate, the radial operator, which way how I was asking, is it related to the radial momentum operator? I believe you can think about it that way. D minus 1, R, D minus 1, dr, x psi. Okay. And then, this is where you get the orbital angular momentum. It's 1 over 2 r squared, x, and then j, I, j, j, I, j. psi. So this is the sum over ij here. Okay, so this is in all dimensions d greater or equal to 2. And if you do it in 3 dimensions, which is what we're going to do most of the time, it would be, you just plug in d equals to 3, so it will be 1 over r squared, dr, r squared, dr, plus 1 over r squared, and then this will be x j squared. So this, well, firstly, j squared means ja, summed over a, meaning what you will find is that if you sum over these guys in using this double index operator, in 3 dimensions, 1/2 ji you would find is equals to ja. Okay, so this is the case for 3 dimensions. And in particular, this is also, in fact, equals to minus, you will find, this is equals to, I'm sorry, this is a minus. This will be, in fact, minus xi partial j minus xi partial j squared. Okay, acting on x side. And this is something that you're going to prove in your homework for arbitrary dimensions in fact. So again, linear momentum is related to angular momentum when you square it. Okay? When you square it, you get the Laplacian. This is just partial I in Cartesian coordinates. But when you re-express it in spherical coordinates, okay, then you get this. This is Cartesian. This is spherical. You get r theta phi. And that's how you see that this will split up. And so I should say this is purely angular. Purely angular. Okay. It doesn't look like it because you have Cartesian coordinates here, right? But if you write it out, and if you also remember, this generates rotations. Because it generates rotations, it cannot depend on r. It cannot have r derivatives because you're generating rotations on the sphere, which means that you cannot be moving in the r direction. Okay. So what you discover for yourself is this important insight, the relationship between linear momentum and angular momentum from the linear algebra point of view. Yeah. Good question. Somebody is whispering here. You have a question? Yeah.
The first one, your first one.
This one?
It's ji plus.
Yeah.
When you go to the third one, it becomes minus.
This one goes to this. Why this became a minus?
Yeah.
Is that what you're asking? Yeah, so remember this is omega ij with a minus sign, right? Because it's antisymmetric. Yeah, remember the generators of rotation. So on the left-hand side, on this side, I'm just applying the ordinary rotation on the coordinates, right? And remember, we proved that rotations can be written as exponential of an antisymmetric matrix. You remember? And so this is just an arbitrary antisymmetric matrix. Yeah. Yeah. And I think my sign error showed up here, actually. I think if I put in a minus sign here, because what I want to do is I want to say that these are my parameters. This is a matrix, right? But when I reduce it to a parameter, I want my rotation angles to look like this: cosine theta minus sine theta, cos theta. And this is how I remember this. So for small rotations, this is identity, and then I pull out a minus theta. This theta are these omegas here, right? So and then this will be 1 minus 1, 0, 0. And these guys are my generators, right? These guys are my generators. So if I want to match it up, I think what I need to do is I need to stick in, I need to do this actually. So let me fix it right now, actually, otherwise I forget. So what I need to do is, I need to actually write the following. I want to say that this is actually minus omega ij, and then divided by 2, contracted with j hat ij. So omega hat ij is actually minus omega ij, j hat ij. Okay, but I claim, if you write this out, so remember that j hat ij itself, in fact, probably I need an I here, if you write this out, I claim that this will just become minus omega ij. Okay, that's my claim. Because these guys are these guys here, and so it will just turn out to be minus omega. So this will become minus without the hat. This is just a bunch of parameters contracted with this. And then with the minus sign, this will be minus sign, and then this will be minus sign. I'm sorry, this is not minus sign. This is the operator version. This is the minus sign. This will have a minus sign. And so by the time I get here, this will be a plus sign, and it will be correct. Okay. Remember, my convention is always, I have a minus sign, plus sign, but I like to pull out the minus theta, and this will be my generator. So what will happen is that this will be a minus sign, and yeah, so that's where my error came. Right, then it's correct. Okay. Good.
Sorry, I have
Yeah,
a question.
yeah.
So why there is a partial undefined second
Sorry,
second?
yeah, sorry, no. I want to just define the rotation, but here I'm doing an active coordinate transformation, meaning I'm taking R and I'm applying it to X. So it's the same X on the right hand side. I shouldn't have an X prime.
Okay.
Yeah, good. So, what's this all got to do with quantum mechanics? So the first thing to note is the following. Okay, so to connect back to quantum mechanics, what you will show, one of the things you will show in your homework is that we can identify compatible observables. Okay, compatible. And this part will be very important in all kinds of applications. Whenever you have something like the angular momentum, remember that these guys themselves, now we do it in 3D, right? Because that's what the thing that we care about. Remember that they obey this Lie algebra in 3 dimensions. What you will discover is that because these don't commute amongst themselves, you cannot, in fact, use all of them as compatible observables. They don't commute with each other. But what you can show is that in arbitrary dimensions, the JAB in fact commutes with the square of itself. Okay, this is something that you can show directly from the Lie algebra. Right, so from this, from the d-dimensional version of this is only for 3D. What you discover is that for the d-dimensional version of the Lie algebra, you can show this directly when you commute. Okay. Physically, how you should think about this is that this is a scalar. Okay, because you're dotting the generator with itself. It's a scalar. This generates rotation. So because it's a scalar, it will commute with this rotation generator. And in 3 dimensions, what you will say is that this amounts to saying that JA commutes with J squared. Right? Again, remember J squared in 3 dimensions is equal to this quantity here. So this is, and JA has a one-to-one correspondence with this JAB. So therefore, in 3 dimensions, this is the same as saying this. So that means we can identify the following observables. We can say that we can identify whenever you have rotational symmetry, whenever you're rotationally symmetric problems, you want to identify simultaneous eigenstates of J squared and one of these J's. And usually we will take the third component. So we want simultaneous eigenstates of J squared and J3. Okay? And this is where spherical harmonics come in in many instances. But it's more than that. But let me do spherical harmonics first. Okay. It's more than that because from this angular momentum algebra, what we'll discover is also the more abstract concept of spin. Okay. Just from this alone, we'll only do 3 dimensions from now on. Just from this alone, you will discover the concept of spin. And spin is not just, in particular, it's not just angular momentum, orbital angular momentum, but you also have intrinsic spin 1, spin 2, and also spin 0, and also spin half particles. Right? The math will allow for any arbitrary spin half. But as far as fundamental particles are concerned, we only know of electrons. Right? They're composite hadronic objects in nature. But in terms of composite fermionic hadronic objects in nature, they have higher spin, spin 3 halves and so on. But those are not fundamental particles. They are built up of the fundamental spin half particles that we know, the quarks in particular, can form bound states to give you these higher spin fermionic hadronic states. But we will get there. Hopefully by Thursday, I will show you how from these algebraic relations you can get spin half. Or maybe if we move fast enough, we'll get to it by today. But first I want to talk a bit about spherical harmonics. Okay. So spherical harmonics can be introduced in different ways, and I will show you two slightly different ways to do it. So first thing is, all right. So what I think I'll do is I'll continue with this discussion because since we started, let me just keep with this discussion in terms of the polynomials, okay? And then I'll return to the more abstract but more comprehensive way to deal with spherical harmonics in a little bit. But the key to all of this discussion, remember, is the angular momentum operators. So remember that JAB, which is epsilon ABC JC, can be identified with the derivative operators minus I x A partial B minus x B partial A. Okay? And in particular, if you ask how does in your homework, you're going to work out all of them in spherical coordinates. Okay, but let me just write down for you what the third guy would look like. So in spherical coordinates, this would be just minus I d phi acting on theta phi psi. Okay? And remember that the compatible observables are J squared. We've chosen J squared and J3. So which means that, well, we've diagonalized J squared. We have in fact diagonalized it by recognizing it as the angular part of the homogeneous Laplace equation, which gave us the eigenvalue L times L plus 1. Okay. But what about J3? So J3 requires that we basically solve this equation, right? You have theta phi psi, and let me just call it M minus I d phi is equals to, so if J3 acting on M is M times M, meaning it's eigenvector, then it means that I need to obey this differential equation. Yeah? Because J3 this is in fact theta phi J3 M, and J3 acting on M gives you M. So therefore it must obey this differential equation. What's the solution of this equation? It's just an ordinary differential equation. Exponential, right? So therefore, you don't need to know how the theta part depends how it acts yet, but you know that this guy has to be proportional to an exponential. In fact, e to the I m phi, right? And because when you take minus I d phi and you differentiate this guy, it brings down m. So we're making some progress here. We realize that we know the eigenvalue of J squared, and now we've also identified the eigen vector of J3 in this position basis. But more than that, because this is a function, a complex function of phi, again, if we want our boundary conditions to be such that phi plus 2 pi must bring us back to itself, if this is our choice, then you see that this means that e to the I 2 pi m must be equals to 1. Okay? So you need to come back to yourself. In order to come back to yourself, this guy must be 1. And for this to be 1, therefore m must be integer. Integer. Okay. So it will turn out, and this is the part that I won't be able to prove right now, but it will turn out that it's not only an integer, m will turn out to lie between minus L and L. Okay, but we'll prove this in a more general way later on. But for now, I'll just have to tell you that it will turn out that it's not only an integer, but it's an integer that lies from minus L to L. Okay? And so this gives you a strategy to, in fact, construct these, spherical harmonics, which I will tell you about now, before we move on to the more general construction. Okay? So whenever I want to emphasize that these are eigenstates, I will use this bracket notation, right? So this is the eigenstate of J squared. And we've also discovered that it's also the eigenstate of J3. What we haven't proved, but I will, hopefully by the end of today, is that m is an integer that lies between minus L and L. So what we have also shown, and this is where the Ylm notation comes in, is that when I view it as a function of theta and phi, this is basically saying that is the eigenstate Lm, but written in the position basis. Right? For the most part, I'm going to suppress R, but you can think of this as a three-dimensional function. It's just that I don't care about R. Okay. So when I don't care about R, then it's just a spherical harmonic. Now, what we have shown is that minus I d phi acting on Ylm is always going to give me m. This is just this guy written in the position basis, Ylm. And I also know that the angular angular Laplacian minus Laplacian on S2 acting on Ylm must be equals to L times L plus 1 Ylm. Again, this is just this guy written in the position basis. And finally, we also know the Laplacian in 3D acting on R to the L, Ylm must be 0. Okay? So these are just eigenvalue equations. This guy is where we started, actually. But using all these properties, I'm going to show you how we can, in fact, construct the Ylms explicitly. Right? So remember that this is now the way we started originally was that this is a polynomial of the homogeneous degree L. Okay? So we can go L by L and make sure that we can satisfy all of this. So let's keep this in mind in particular. Okay? So the fact that this is true means that all the Ylms must be proportional to exponentials of phi. Okay? So that makes it easy to remember, because instead of x1, x2, x3, remember x1 is r sine theta cos phi, x2 is r sine theta sine phi, and x3 is r cosine theta. Instead of this, I want to get exponentials out of this. So the first thing I'm going to do is I'm going to take these guys, I'm going to define x plus minus to be, remember I didn't say that these guys must be real, right? It just has to be degree L. I didn't say it has to be real. So I can always take x1 plus or minus I x2. And you see what will happen is that now I get r sine theta. This is the common factor between them. And then I get cosine phi plus or minus I sine phi, which tells me this gives me r sine theta e to the plus or minus I phi. Okay? So every power of x plus will give you one power of e to the plus I phi. Every power of x minus will give you one power of e to the minus I phi. So therefore, x plus to the 8th power, x minus the 8th b power, you know, has to give you e to the I a minus b phi. Right? And this will tell you how to construct. This is going to be a guide to how to construct n. How to get n, the desired n. But let's do it. Okay, so let's in fact see how we get these polynomials. It's best to just start to do it and then you see how it goes. So the degree L equals to 0 term is just a constant. Yeah? Well, if you apply Laplacian on a constant, it's 0 for sure. If you apply d phi on a constant, it's 0. And suddenly when you apply the Laplacian on the sphere on 0, you get 0. So L is in fact, so L is in fact 0. And in fact, n is also equal to 0. Right? That's not terribly interesting. L equals to 1. Okay? So how do I get L equals to 1? Well, remember it's degree L, degree 1. So I can try either one of these guys, x plus, x minus, and x3. Okay? So what you discover is that when you add d phi on this, you get this is e to the I phi. This has e to the I phi, this is e to the minus I phi, and this is e to the I0 phi. Okay, and so you can do a direct calculation to show that this, for this n equals to plus 1, n equals to minus 1, n equals to 0. But do they obey this, for example? Okay, so, and you can show, this is, remember, partial I. You're differentiating the coordinates twice, but there's only one of them, 1, 1, 1. So L equals to 1 is very easy to construct because when you differentiate twice, all of them are guaranteed to vanish. So all of them must satisfy this equation, and therefore all of them must be spherical harmonics. Okay. Now, the only thing left is this guy. And you can also, again, do a direct calculation and show that this is, in fact, L equals to 1. Okay. So, in fact, I should mention, this is, in fact, one way to see why n can only lie between minus L to L. Because you remember that the maximum power is L, right? So the maximum number, so that means that maximum A max is L, and B max is also L, right? Because that's how many total powers you have. So if you have all the powers are in x plus, meaning you have x plus the L, you cannot have any more powers of x minus, you cannot have any more powers of x3, because that's the maximum you can have for a fixed degree L. But if you have x plus to the L, that means you have e to the IL phi, which means m is phi. And so that tells you that the maximum m is L. You cannot have more than that because this is the one that increases, this is the one that has positive powers of e to the I phi. Right? That's how many you have. If you have B max equals to L, that means that x minus is L, and you cannot have any more x plus or any more x3, but that means you have the most power of e to the minus I phi, which means that m is now the least possible value. Right? You cannot have anything less, because anything less will require higher powers of x minus, but you can't. You already saturated the most number. So that means, so this means that n max is plus L, and this in fact means n min is equals to minus L. Okay. So you can see explicitly that having more and more powers of this will give you more and more m's, higher and higher m's. Having more and more this with x minus will give you lesser and lesser m, smaller and smaller m. So maximum m is just as many powers as you can for this guy. Minimum m means you have as many powers as x minus as you can. Right. So I thought I should mention this. This is why n lies between minus L and L. But like I told you, we're going to prove it in a more abstract way later on. But let's continue with this. So what about L equals to 2? Okay, so the first thing is L equals to 2, well, we already just said. How can you get m equals to 2? X plus squared, right? So up to a normalization, this is x. It must be that. You can't have anything else, okay? Because that's how you get m. And you can check, and you should apply the Laplacian on this guy, and you discover that in fact it would be 0. Okay, you should check. And likewise, you can get m equals to minus 2. How do you do that? I must square what? X minus. Okay? And then, in between, m equals to 1. Now I must have either x plus, I must have x plus, but then I need one more guy, so this must be x3, right? And then m equals to minus 1, what do I get? I must have x minus and then x3. Okay? You can play around. If it's not clear to you, just play around. Put some powers of x plus and x minus to get the n that you want. But you must constrain it so that it cannot exceed L. Right? A minus b must lie between, must be less than or equal to L. Right? So in this case, you discover you cannot have 2 powers of this and 1 power of x minus, for example, to get m equals to 1. You just can't have that. So the maximum power you can have is x plus. Right? And again, you can check that this guy will satisfy this equation. Okay. The trickiest part is actually this guy here, m equals to 0. Okay, the trickiest part is because you can have x plus, x minus, right? Because these will, the exponentials will cancel to give you m equals to 0. But you can also have x3 squared, right? x3 simply doesn't have any x3 simply doesn't have any exponentials at all. So it must be a combination of these guys, right? And this is where I think we need to do a calculation. to figure out. So let's do it in fact. So A times x3, x plus x minus plus b x3 squared. Firstly is A, remember the x plus minus is this guy, so it's x squared, x1 squared, and then minus, and then it's actually plus x2 squared, right? Is alpha minus beta squared, but beta is minus, is actually I2 squared, so it becomes a plus b x3 squared. And I write this in this way because now if I apply the Laplacian on this object here, a x3 x plus x minus plus b x3 squared, what do I get? I get that this is now a 2a, right? 1 plus 1 plus 2b. Did I do it right? And this is equal to 0. Okay? So this is now 4a plus 2b equals to 0, which means b equals to minus 2a. So up to a normalization, I realized that the L equals to 2. Let me draw it properly. Let me do, this is L equals to 0, L equals to 1, and then L equals to 2, n equals to 0 case is actually equals to b equals to minus 2a, right? So I can pull out the a, I can forget about the a, plus minus 2 x3 squared. Okay? Up to a normalization. Now, normalization-wise, because this is basically a function of a sphere, and the volume of the sphere, the surface area of the sphere is 4 pi, so what we usually demand is that Ylm, we demand our eigenstates to be normalized to 1. So if you insert the position eigenstates on the sphere, what you'll be doing is this. Yeah, this is just an insertion of the completeness relation on the sphere. And so that just means that, so the notation for this is just a integration measure on the sphere, is the solid angle, and this in turn is the spherical harmonic conjugated, so Ylm star times Ylm, so it's Ylm complex absolute value squared. This must be equals to 1. So once you have the polynomials, once you have these polynomials, you can factor out the r squared, right? So this will be r squared times some angular dependence. This is also r squared times some angular dependence. So it will be this, in this case will be y22 times some number. This will be y21 times some number, and so on. So the way you normalize it is to just do this integral and make sure that the angular part is normalized to 1 when you integrate, when you square it and integrate over the sphere. Okay? So I think in your homework you might get to practice on a few of these spherical harmonics. And you will also get to work out the L equals to 3 case. Okay. So L equals to 3 is a bit more complicated, but it'll give you a chance to play around with these guys. But otherwise, it's just counting powers of x3, x minus, plus to get the right amps, and then checking that the homogeneous equation is satisfied. Right? That's what you would discover. Okay. Any questions for me? So that's one way to think about spherical harmonics. Just pure by pure construction, essentially. Okay, but by pure construction, starting from the perspective that they are homogeneous polynomials of degree L. But now let's take a more abstract way to get that. Okay, and how do we do that? The way we do that is through looking at the Lie algebra, as I've said. Okay. Oh, I guess I should also say one more thing, which is that before we do the more abstract approach, there's a closely related way to solve the equations that I just wrote down, which is that you can certainly write down the Laplacian on the sphere. So we wrote this down the other day. And this is how you would do it in electromagnetism, actually. So if you open the textbook by Jackson, you would, in fact, go ahead and solve this. So you already know that this guy has to be, because it also obeys d phi equals to m Ylm, you already know that Ylm itself must be proportional to e to the I m phi. Right, so this you already know. And so what you then do is you plug in, you use what's called separation of variables, and you plug in and you plug in for Ylm the exponential times cosine times the function of cosine theta. And so what remains is to solve for this. When you plug, and then this is now I epsilon 3, 1, 2, J2. Remember this guy over here, plus or minus I squared, I from here, one more I from this commutator, epsilon 3 to 1, J1. So this is 3 to 1, so I've got to swap, I've got to move 3 two places to the right. That doesn't cost me any minus sign, so that would be just equals to epsilon 1 to 3, right, which is equals to 1. This guy is, I'm going to swap 1 and 2 first, and then I swap 3 to the right twice, so I get minus 1 epsilon 1 to 3. So that gives me I J2, and then this guy is plus or minus, I squared is minus 1 times minus 1, so you get plus or minus J1. So again, I can pull this out and get J1, plus or minus J1 plus or minus I J2. Okay, plus times plus is plus, minus times minus is plus. Right, and so that means that I can summarize this as J3 commuted with J plus or minus is in fact J plus or minus J plus minus. Okay? So why is this useful? Let's say I start with the eigen, so in my notes I call it lambda, but since I already introduced L, I'm just going to go with L. So I know that okay, maybe I should stick with lambda. So let me just do that. So let me call this lambda. So we already know that lambda is going to turn out to be L times L plus 1, but let me just stick to what my notes say. So for now, lambda is just the eigenvalue of J squared, and J3 is going to be M. Okay. So let's take one of these guys and apply either J plus or J minus to it. Let's do it here. Let's consider J3 applied to J plus or minus acting on lambda M. What would this give us? Well, let me try to commute through. So I will take J3 commutator J plus minus. So this is J3 times J plus minus minus J plus minus J3. So I need to add J plus minus J3 to cancel out the second term in the commutator. Okay. If it's not clear, just expand this out, and then you see the second term will cancel this second term, the M. Okay. And so for the reason for doing this is now we know that this is plus or minus J plus minus. We calculated it over here. Plus J plus minus J3 acting on this. Remember, this gives you M. Lambda M. Okay, so now I can pull it all out, and I can say that this is M plus or minus 1 acting on J plus minus lambda M. So i.e., in words, what does that mean? It means that J plus minus lambda M is eigenvector of J3 with eigenvalue M plus or minus 1. In other words, J plus minus lambda M is up to a constant, which I'm going to call M plus minus C M plus minus 1, lambda M plus or minus 1. Okay? The reason why I have to put a constant here is because we normalize our eigenstates to 1. Right? When you take the inner product of the eigenstate with itself, is 1 by definition. So this may not be normalized properly. In fact, we'll discover what this is. We'll need to solve for Cm in a little bit. But for now, what we have determined is that it must be proportional to n plus 1, because we just calculated it. Okay? And remember, this technique of introducing a ladder operator shows up all the time. It's not specific to rotations. In fact, it shows up all the time. So, in fact, I think in a few weeks we'll see it again when we do the simple harmonic oscillator, the quantum simple harmonic oscillator. Okay. So, in fact, now let us figure out a bound on these lambda. Okay, so from the spherical harmonics, we kind of know how they're related to m. But let's see that it's more general than that. Okay, we'll discover now the more general perspective to this lambda. And we're about to discover the notion of spin. So how do we do that? So let's consider the following object. Let's calculate j plus minus dagger, j plus minus. Okay. And what this thing would tell you is that this is actually j1 plus or minus j2. But remember, these generators are Hermitian. So this will give you j1 minus plus I j2 because of the dagger. The plus minus becomes minus plus, but the j's remain the same because they're Hermitian. And then we have j1 plus or minus I j2. Okay? And this, in fact, is just nothing but, let's multiply it out. In fact, this is j1 squared, and then this guy multiplied by that gives you plus j2 squared. Remember, these are operators, so I can't just use the algebraic formula, right? So I have now minus plus I j2 j1, and then I have plus minus I j1 j2, right? So these guys are from this guy and this guy, and then this guy times this guy, just use this guy, right? But now I can write that guy as a commutator. So this is j1 squared plus j2 squared, and then plus or minus I. This is j1 j2 minus j2 j1. Right? This minus will convert the plus minus to minus plus, but this is now commutator. This is now commutator of j1 j2, which is again I j3. Okay, and so this one becomes j1 squared plus j2 squared, and then becomes minus plus j3. And furthermore, I'm going to write it in this way. I'm going to write this as j squared. J squared is j1 squared plus j2 squared plus j3 squared. So I need to subtract the j3 squared here, and then minus plus j3. Just to make it so that this is now j squared, and then the rest is j3. Now, we know that the norm of any state, we know is always greater or equal to 0. Right? This is not necessarily a physical state, it's just a linear algebraic statement. The norm of any state is greater than 0. So if I consider taking the 1/2 of j minus acting on lambda m, right? So this is nothing but just the norm of this vector, j minus acting on lambda m, plus 1/2 of j plus acting on lambda m dagger, j plus acting on lambda m. Again, this is just a norm. It's just a norm of this vector, j plus acting on lambda m. Therefore, this whole thing must be greater or equal to 0. Just following from this, right? But let's calculate what this is. Well, this is now 1/2 of j lambda m, right? It's the same thing throughout, so I'm just going to write it like that. There's common factor of 1/2, and the bra and the cat are the same, except this is now j minus dagger, j minus, plus j plus dagger, j plus, okay? Again, it's greater or equal to 0. But we calculated what they are, right? So if it's j plus, we'll get a minus sign. If it's j minus, we'll get a plus sign. So when I add them, this term will cancel out. Yeah? This term will cancel out. And actually, that's why I do that. And so, in fact, what we see is that lambda m j squared minus j3 squared, oops, must be greater or equal to 0. Okay. So it makes intuitive sense because j squared is like the vector, the total vector squared. This is only one component, right? But remember, this is also an operator statement. These are operators, so it makes intuitive sense, but you must make sure that you prove it, right? Otherwise, it's not just a vector statement. It's an operator statement. But now you see, we're using these eigenstates exactly because this guy is supposed to act on this and give you lambda. And this guy acting on this will give you m squared. So therefore, lambda must be greater or equal to m squared. Whatever lambda is. Remember, I still don't know what is lambda, right? I still don't know what is lambda. So let me finish and then I'll let you guys go. But here's the logic, okay? So we have just seen, so let me not erase this part. But we've just seen that the j plus and j minus will give me lower or higher m's each time I operate on the eigenstate. Yeah? So if I start with, right, these two guys are independent, right? So that's the main point. These two guys are independent. So if I start with, for a fixed lambda, I can keep going. I can apply j minus n times on lambda n, and this should give me lambda n minus n, right? Well, that means that I can keep going. I start from m squared, then I go to m minus 1 squared, then I go to n minus 2 squared. I can keep going. Remember, it's a square, so this can get as large as I want. Yeah? I can go, it can be as large as I want. Remember, because it's a square. So I can just keep lowering and lowering. Same thing. If I can keep raising. Remember, this is lambda n plus n. So m squared will go to n plus 1 squared, go to m, if I raise another time, so this means j minus, and so on. This means j plus, and so on. So if there were no n to this process, then I must be able to violate this bound. Yeah, because I can keep doing it. This is supposed to be smaller than lambda, but lambda is fixed. But now I've just managed to violate it. I must be able to violate it because n minus infinity squared is infinity, right? Or n plus infinity squared is infinity. But that cannot be less than lambda. Right? So that's a contradiction. It's a contradiction. Contradiction with the bound lambda greater or equal to m squared, right? Unless the series terminates, right? So unless there is in fact a minimum, what happens when you add the lowering operator on the minimum? It must give you 0. That's how you terminate the series. if it were not 0, that would mean you will get n minimum minus 1. And then you won't, then again, maybe you can violate this bound again. So it has to terminate. If it gives you something non-zero, that means it doesn't terminate. So same thing for the raising operator. There must be a maximum where when you add the raising operator on it, it must give you the 0 vector. Again, otherwise it won't terminate. So IE must terminate. This process must terminate somewhere. Okay? But we know how this thing acts. Okay? We know how this thing acts. And maybe I'll do this the next time. But this is where, let me just tell you the punchline. Okay? So what we'll discover is that M max. So next time, we will discover the following fact. The M max is equal to minus M min, to the just opposite signs of each other. And this is in fact what we call L in our previous notation. And so now, n lambda itself will be in fact L times L plus 1. And moreover, we'll discover that this is in fact what we call spin. Spin is in fact the maximum eigenvalue of J3. And moreover, we'll discover that L, which is the maximum eigenvalue of J3, can be integer or half integer, 1/2, 3/2, 5/2, and so on. It just comes out of the algebra, right? We just from the angular momentum algebra, we will discover that we're allowed both integer and half integer spin, and that will in fact lead us to search for, in particular, where are these 1/2, 3/2 states? Where do they come from, right? And what do we do about them? And that's in fact, in nature, that leads us to things like the electron, right? The proton, the neutron. So in fact, these spin half states do in fact exist. And we could have predicted their existence if just by studying the properties of the rotation group. Okay. Any questions for me? Yes.
So at graduate level, we know quantum mechanics, like creation operator and annihilation operator, they are related to P and X. So here J is something related to.
Yeah, so the algebraic properties are similar, but they're not the same thing, because what you're talking about there is the simple harmonic oscillator, right? The P and X. So we'll do that. We'll also do that. But in this case, we're talking about the generators of rotation. So the meaning of the operators are different, but the algebraic commutation relations are very similar. That is true. Yeah. So when we come to that again, you will see something very, very similar will happen as well. But those operators will excite the harmonic oscillator states, right? Those will bring you from one energy state to a different energy state. Whereas these guys bring you from one angular momentum J3 state to another J3 state. Right? So the meaning, in terms of the meaning, is a bit different. Any other questions? No? Okay, see you guys on Thursday.